Hello, it is Robert Guderian, and we have one more lecture on slicing this week before we start to talk about two-dimensional arrays next week. So, we're going to be slicing the pie. Okay, so we have seen normal slicing works. That is something that's not too surprising for us. That we can just say, give me from the fifth index all the way to the end, and it will do that for us. And this code runs and works, and it's not anything too surprising for us. I could have a predict the output, and you would say it starts at legitimately 5 and goes up to and including 10, and that's what it'll be returned. Okay, good. So, we've also seen we can do operators on an entire piece of data. So let's actually see this. My data is equal to np.arange starting at 1 and going up to 12. Fun change. Get a full dozen. And then I can print out my data. And as predicted, it works as you would expect. It goes from 1 up to and including 12. And then we can, of course, slice this. So we can do the same slice we saw where we start at 4, sure, and go up to and include the end. And that worked. Fantastic. Exactly what we'd like to see. So we can also add 10 to every single value in our Numpy array. So I could say data plus 10. Okay, cool. It'll do that for me. Well, what if I said something like this? So data, starting at 4, going up to the end, and then that plus 10. What's the order of operations here? Well, we can just test it, of course. It will do the slice first, and then add 10 to that shortened slice. And we have to start thinking about what is actually being returned by these slices. I'm going to move this over to here so I can just run it interactively. Data 5 up to the end. Well, we can, of course, test this, where I can store this in D, and then we can say type. We probably haven't seen this from the first week. It'll tell us that it's an NumPy ND array, so it's an n-dimensional array. The number of dimensions is, of course, 1 at this point, but it is an n-dimensional array, just one dimension of it. So that's neat. And our variable explorer actually will show us some stuff too. Oh, my kernel's a mess. I'm going to restart my, whoop. Sure, remove all variables. That'll actually work for me. I can restart and run. There we go. Nice. Now, can we do even fancier things? Well, yes. So the whole, one of the beautiful things about, this one, we've seen inequalities too. We can do an inequality on the entirety of an array, and that inequality will return us a NumPy array of Booleans. So remember that we're always getting NumPy arrays back. We're always dealing with these arrays at every step. So I can say data is greater than 4, and it's going to return me an array that is the same size. So there's 12 trues and falses here as our initial array. Let's actually shrink this down to 5 so we can see this a little bit clearer. And then rerun that. And we can see that 1 to 5, which will give us 4. Let's start this at 0. This is actually baffling. Don't ever index at 1. It's a terrible idea. Oh, wow, that's the meme. That's the meme at the end of the slide deck, too. There you go. We have five data elements. They're all false. And that's okay. We can actually see our data, and we can see that, yeah, it's all less than 4. So let's maybe even say greater than 2. And then we have some trues in there. Okay. And that's not too surprising for us. We knew that we found out that we can store this as some kind of list of Booleans. And then we could say bools.sum, and trues will be 1s, falses will be 0s, and we can get the sum. Oh, that's neat. That's nice. That's a nice tool. Okay, great. NumPy seems fairly useful. But we can also slice with a list. And this feels a little scary at first, but we just have to remember that we're always dealing with lists. So the idea here is that we have some list of data where we can even have that same list, 0, 1, 2, 3. And then we can have an inequality to say, is this list item greater than 1? And that's going to return us a NumPy list array. It's an array of Booleans. Is 0 greater than 1? No. Is 1 greater than 1? No. Is 2 greater than 1? Yes. 3 greater than 1? Yes. Then what we can do is use this as a slice. I believe I called this the slice list in the slide. So I'll stick with that parlance. That is a Rob special. And what we're going to do is only keep the ones where the Boolean is true. So this, if we sliced saying where my data is greater than 1, it would return a NumPy array of just the numbers 2 and 3. It'll be just this stuff. There's a few keys here. This list has to be, these two lists really have to be the same size, same length. Otherwise this falls apart. I think I call it like an index mismatch or something in the error. It's a nasty error. You don't want to see it. They have to be the same length, period. That's it. So what does this syntax look like? And this is where things get interesting. The syntax is ugly. So I'm just going to copy this out so we can just play with it and put that into my fancy spider over here. Data is, I'm going to index this at 0. It's not 10, 0. And then our shortened list is where data is greater than or equal to 3. Ugh. So what's happening here? I said that we're slicing on a list of Booleans. Data greater than or equal to 3 will return me a list of Booleans. And we can prove that to ourselves. We can say, is data, boom. Hey, it's an array of Booleans. Fantastic. And we're going to pass that in as a slice. And that is why we're using these brackets. We're still using the square brackets to do indexing. Then I'm going to print out short. And it will indeed be shorter. So let's see the data going in and data going out. That's always a good idea. Perfect. I can abstract this out more. I'm going to do this here, where I can actually, and this is weird syntax too. It's a list of Booleans is equal to that. Well, we know that this is going to return a list of Booleans, so why can't I store that in a variable? Well, I can. Of course I can. Some people like showing it in brackets so that the order of operations is a little clearer. It'll always look weird. It's true. But if we're doing an inequality, it's going to return us a list of Booleans. And then I can slice on that list of Booleans, provided it's the same length as data. And in this case, it is. So it'll work. I can even print out my list of Booleans now, too. Lust of Booleans. I really like these Booleans. Not a function. Spider's trying to help me, and I'm not letting it help me properly. There we go. So here's my list of Booleans, and you can see that I am indeed only keeping the last two indexes. And then that is in my slice. The syntax just gets a little bit of time. It takes time to get used to. Just always do this, and it feels better. Breaking it out is good for your mental state, but not good for programming. So, consider what percentage of dice rolls are over 12. So these are, of course, D20 dice rolls because you're dealing with me. And we can easily say, give me a whole bunch of D20 dice rolls. I said 10 of them. Then give me the slice where my dice roll is greater than 12. That's it. All I have to say is, give me the slice of where this is greater than 12. So if I can jump back to my spider, I can print above 12. And then run it. And hey, look at that, it'll work. There is not 10 rolls here. Half of them, wow, that's impressive, are above 12. So that's actually statistically pretty good for me. And then, well, what is a percentage? We want the number that are above 12, and I literally have that in a list. So the length of that list is the number of rolls that are above 12. And the number of rolls I did, what is in length of dice. So all I have to do is add this to my code, and this will change every time because I've not set a seed. 50%, 60%, 30%, 60%. I could multiply by 100 if I wanted to view this as a normal human being. There you go. You can even put in a percent sign. Format this all we want. I know we're all tired of formatting. I'm going to actually say 0.0 because that's ugly. Well, yay. Cool. Cool stuff. Neat. So that is a beautiful, just little slice. And we're storing that sliced amount because this returns a NumPy list into a variable. This returns a NumPy list as a theme. Keep that in mind at every step here. What are the rolls? Well, we could actually print them out. Just print above 12. That's it. I think did I do that? I already did that. I know where I'm going with this. Can we update rolls? Well, yeah, we can. This is the exact same thing what we saw before of saying, well, we can do a mathematical function on an entire list or array. It's an array. Sorry, I've trained myself to say list. So now I'll do this over here. Dice, where the dice rolls are less than 12. Well, it might as well be 0 because you're not going anywhere. And equals 0. This is an assignment. You'll note. I'll actually pull this out. You'll notice that I'm assigning. There is an equal sign here. So if I print dice, I've actually changed it. But I'm only changing it where the dice rolls are less than 12. And you can see that I now have zeros for any numbers that are less than or equal to 12. Huh. Well, that's neat. Well, what if I wanted to do math on the numbers and only assign those certain numbers? We can do that. The arrays must be the same length, but we can have a slice, so we can assign to a slice, given a slice, and do that some math to it. So I'm making them negative. Multiplying by -1 will make my dice rolls that are less than 12 negative. So I'm going to get some new dice rolls because I've ruined that list. And I'll print out my dice. And now any dice rolls that are less than 12 is going to first find that slice and then multiply that slice by -1. And it's going to be a list of size. If n is the length of our list, this is of size m. We are not certain what it is. M's range is from 0 up to n. So it could be nothing. It could be the entire list array. We don't know. Then we're assigning that back to a slice. And as long as these two arrays are the same length, we will assign. And if they're not the same length, bad things happen. Actually, let's break this. That should do it. Or you can see the assignment. You can see the anything less than or equal to 12. I'm seeing the 12 being negative is negative, and then I have 16 and 13, which are not negative. Now I've ruined this. This is the less than 1. There we go. If your two arrays are not the same length, this is the error message you get. NumPy Boolean array indexing assignment cannot assign 0 input values to the 6 input values where the mask is true. That is probably a true statement. What they're trying to say is you are trying to assign 0 numbers to 6 numbers. We can't do that. We need, if the slices are both 6, which it seems to be, we need 6 numbers in the input array and 6 numbers into the slice. where we are assigning it. If that is not true, we can't do it. We're going to give up, and we're going to throw a very nicely multicolored error message. We could also do this in place. So using that times equals, plus equals, times equals, divide equals, minus equals, is assignment to the variable. So this is a little bit cleaner, right? Where we have an array and we're going to take these numbers and update them in place, which is beautiful. There's a difference here between these two things. This will probably not affect your life at all. This slide right here, there's only one array that exists. In this slide, oh, it's this, that'll actually be the same. Sorry, nothing. It's so confusing that even I just got it wrong. Okay, so summary. There's a few ways to do really neat things. Slicing is powerful and fast. This slicing stuff is ridiculously fast. You cannot program it to go this fast. You just can't, not with Python. And we can do conditional slices, which is super cool. And everything returns a NumPy array. Always, always, always. Which is very important to making sure that our sanity stays in place. Thank you for watching.